Hello friends, I welcome you in lecture number 42 on double integrals. In this lecture also we will discuss one more example on change of variables in double integrals or on substitution in double integrals. So first we understand what is this example. Evaluate double integral of x square plus y square over region R, which is the region in the first quadrant and bounded by the hyperbola x square minus y square equal to 1, x square minus y square equal to 9, xy equal to 2 and xy equal to 4 by changing the variables. So here we are given the region R, which is bounded by these four hyperbolas, and from these equations we may have the idea about the substitution or about the transformation of variables. Here variables are x and y, and we have to change these variables to new variables u and v. So what will be the expressions for u and v in terms of x and y, that we can have the idea from the given curves. So if we observe, we have x square minus y square in these two hyperbolas, and in these two hyperbolas we are having x into y. So we can consider the transformation. We can consider x square minus y square equal to u and x into y equal to v. So let x square minus y square equal to u and x into y equal to v. So using this transformation we are changing the variables from x, y to new variables u and v. So now here it is not necessary to sketch the region of integration. Why, that I am explaining. Suppose I consider these two curves, x square minus y square equal to 1 and x square minus y square equal to 9. And if we use this transformation, if we take u equal to x square minus y square, we will obtain u equal to 1, and here we will obtain u equal to 9. So corresponding to x square minus y square equal to 1, the curve in UV plane is the line u equal to 1, and corresponding to this hyperbola we are also getting this line u equal to 9 in the UV plane. Similarly, corresponding to x into y equal to 2, we will obtain v equal to 2, which is also a straight line parallel to u axis in UV plane, and corresponding to xy equal to 4, we will obtain the line v equal to 4. Now if we observe here, we have to consider the region R bounded by these hyperbolas in the first quadrant only. And if we observe here, here we have 1 and 9. So from this we can have the idea that limits of u must be in between u equal to 1 and u equal to 9, and from these two lines we can say that limits of v will be from v equal to 2 to v equal to 4. So region we will obtain in the UV plane, that will be the rectangular region bounded by these four lines. And if we have rectangular region, the limits of integration will always be constants. So limits of u will be from 1 to 9, limits of v will be from 2 to 4. So we are able to obtain the limits of integration for u and v directly without sketching the region of integration. Another thing is, we will require the Jacobian of x, y with respect to u and v. We know that J is given by Jacobian of x, y with respect to u and v. To find this Jacobian, we require expressions of x and y in terms of u and v. So one way is we can convert x and y in terms of u and v, and another way is we can use the property of Jacobian. If you recall, I have explained in the first lecture that if we consider Jacobian of u, v with respect to x, y, and if we take product of this Jacobian with Jacobian of x, y with respect to u and v, then this product is always 1. So we can find out this Jacobian because we are having expressions of u and v in terms of x and y, and using this property of Jacobian we can obtain the Jacobian of x, y with respect to u and v. So first we find out Jacobian of u, v with respect to x and y. By the definition of Jacobian, this is a determinant of order 2. First row will be partial derivatives of u with respect to x and y, del u by del x, del u by del y. Second row will be partial derivatives of variable v with respect to x and y, del v by del x, del v by del y. Now we are having expressions of u and v in terms of x and y. U is x square minus y square, therefore del u by del x will be 2x and del u by del y will be minus 2y. So partial derivatives of u with respect to x and y are 2x and minus 2y, and partial derivative of v with respect to x is y, and partial derivative of v with respect to y is x. Del v by del x is y, del v by del y is x. And if we expand this determinant, we have 2x into x, that is 2x square, minus y into minus 2y. So negative negative will be positive, and we have 2 times x square plus y square. We can take these 2 common and we can write this as 2 times x square plus y square. So this is Jacobian of u, v with respect to x and y using the definition of Jacobian. Now we are interested in the Jacobian of x, y with respect to u and v. This is equal to 1 divided by Jacobian of u, v with respect to x and y, and this we have obtained. So it is 1 over 2 x square plus y square, and because x square plus y square is always non-negative, absolute value of Jacobian is also 1 over 2 x square plus y square, because x square plus y square is always non-negative. And because we are considering the region in the first quadrant, region bounded by all these hyperbolas in the first quadrant, x and y will never be 0 at the same time. So this is always non-zero. So once we obtain the Jacobian, and we have obtained the limits of integration also. So now next step is we have to convert this double integral from x, y to new variables u and v. So now double integral of x square plus y square dA can be either dx dy or dy dx. This is equal to I am not converting x square plus y square in terms of u and v, and this dA is either dx dy or dy dx, and that we are going to replace by absolute value of Jacobian times du dv. So dA will be replaced by absolute value of Jacobian time du dv. Limits of integration are u is from 1 to 9 and v is from 2 to 4. So because we are integrating first with respect to u, here we write limits of u from 1 to 9 and limits of v are from 2 to 4. So here we have not converted this x square plus y square in terms of x and y due to certain reason. You can see here absolute value of Jacobian is 1 divided by 2 times x square plus y square. So because I am getting x square plus y square, in the Jacobian also I am not converting this x square plus y square in terms of u and v, because that is going to be cancelled out, and here integral with respect to u and v. So now this quantity will cancel out, and we can take 1/2 outside the integral. Limits of integration: v from 2 to 9, u from 1 to 9. Integral with respect to u first and then with respect to v. So this is equal to integral of 1 with respect to u is u. Limits of u are from 1 to 9. Then we can put the values of u, upper limit minus lower limit. So this is going to be v from 2 to 4, u equal to 9 minus u equal to 1. Integral with respect to v. 9 minus 1, that is 8, that we can take outside integral, and inside the integral we have to integrate 1 with respect to v. This is 4. Integral of 1 with respect to v is v. Limits of v are from 2 to 4. So this is equal to upper limit of v is 4 minus lower limit of v is 2. So finally we obtain 4 into 4 minus 2, that is 2, equal to 8. So we are able to easily integrate over these 4 hyperbolas, over the region bounded by these 4 hyperbolas. Now suppose we are not changing the variables, then it will not be as easy as we have done this problem using the change of variables. If you are not changing the variables, you have to sketch these 4 parabolas. If you recall that equations for parabolas x square minus y square equal to 1, we know that parabola will look like this: x square minus y square equal to 1, and that rectangular parabola will be in this form. Suppose I have x into y equal to 2, and I can sketch another parabolas also. So we will have this type of region. If we are not changing the variables, then we will have this type of region, and here we have to consider sub-regions. We have to divide the region into 2 sub-regions. Either we consider horizontal line or vertical line. So if you are not given that do this problem using change of variables, then also it is advisable to do this problem by changing the variables, because by changing the variables, limits of integration becomes constant. The region which we obtain in the UV plane, that is rectangular region. Suppose this is u axis, this is v axis, then we can see u is from 1 to 9. So suppose this distance is 1, then this line is going to be u equal to 1. Suppose this distance is 9, this line is going to be u equal to 9. If this distance is 2, this is v equal to 2. If this distance is 4, we obtain v equal to 4. So the region in the UV plane is rectangular region, and it is very easy to integrate over rectangular region. Limits of integration becomes constant. So even without sketching the regions of integration, we are able to easily integrate this function over this rectangular region in the UV plane. In the XY plane, we are having the region bounded by hyperbolas. So it is easy to integrate over rectangular region as compared to non-rectangular region bounded by these 4 hyperbolas. So this is the power of change of variables in double integrals. Some problems are very easily solved using the change of variables. So this is all about this session. I hope you like it. Thank you very much.